The next time Mount St. Helens erupts, the explosion will almost certainly be smaller than the one that decapitated the mountain in 1980. Not less violent, not less significant, but smaller. The United States Geological Survey is confident in this forecast. And that is not the good news you think it is. The real story is that the next eruption, even a minor one, could be far more catastrophic for the people living below it. The danger is not that the mountain will repeat the past. The danger is that we have spent the last 4 decades forgetting what it is capable of. As of July 4th, 2026, the official volcano alert level for Mount St. Helens is normal. The aviation color code is green. These are the quietest designations the US-Gs can issue. But here is the detail that tells the real story. Buried in the data from the Pacific Northwest Seismic Network are the tremors of a mountain that is not sleeping. It is inhaling. Between February and June of 2024, a seismic swarm of over 350 earthquakes registered beneath the crater floor. At its peak, the mountain was shaking 38 times a week. More than 95% of these events were classified as magnitude 1.0 or less, too small for a human to feel. But they were not random. They were clustered between 3.5 and 4.6 miles underground, in the very plumbing system that feeds the volcano. In an official statement, the Cascades Volcano Observatory was clear. This was the largest short-term increase in earthquake rates since the last eruption ended in 2008. This was the signature of magma recharge. To understand what is happening miles beneath the ice and rock of the crater, you have to understand the term recharge. Seth Moran, the current scientist in charge at the observatory, explains it as a process of pressurization. Deep within the Earth's crust, a body of molten rock is slowly migrating upwards, pooling into a shallower reservoir. As it collects, it releases gases. It applies pressure to the surrounding rock. That rock cracks and shifts. Each tiny fracture sends a seismic wave to the surface, where it is recorded by a network of silent listeners. Each tremor is a single word in a long message. The mountain is reloading. The system is filling. And every swarm of earthquakes like the one in 2024 is another sign that the pressure is building toward its inevitable release. It does not mean an eruption is imminent tomorrow. Similar, even longer swarms were recorded in the late 1980s and 1990s without an eruption. But it confirms the process is active. The engine is running. A deep geological cycle that has been dormant for 16 years is now audibly restarting. The question is not if it will erupt again. It is what form that eruption will take, and what happens when it collides with the world we have built around the volcano's base. The answer to that lies in the ghost of what happened at 8:32 in the morning on May 18, 1980. That eruption did not begin with fire. It began with an earthquake and a failure of gravity. A magnitude 5.1 tremor shook the north face of the mountain, a bulge that had been growing for weeks at a rate of 5 feet per day. The rock was unstable. The earthquake was the final push. The entire northern flank of the volcano collapsed in the largest debris avalanche in recorded human history. 3.7 billion cubic yards of rock, ice, and earth slid away, exposing the superheated, pressurized dacite magma core within. That is when the blast came. Not upwards, but sideways. A lateral explosion that ripped out across the landscape at over 300 miles per hour. It leveled 230 square miles of dense Pacific Northwest forest. Douglas firs that had stood for a century were snapped like twigs. The temperature inside the pyroclastic flow reached over 600 degrees Fahrenheit. 57 people died. Some were scientists, some were loggers, some were residents who simply could not imagine the scale of the threat. 5.5 miles north of the summit, at an observation post now known as Johnston Ridge, a 30-year-old US-Gs volcanologist named David A. Johnston saw the north face collapse. He grabbed his radio. His last words, transmitted to his base in Vancouver, Washington, became the epitaph for an entire mountain. Vancouver. Vancouver. This is it. Then, silence. The blast consumed him and his post in seconds. He was the first to report it and the first to be killed by it. He understood the science. He knew the risk. He stayed because his job was to watch. Just a few miles away, at his lodge on the shore of Spirit Lake, 83-year-old Harry R. Truman was also consumed. He had become a minor folk hero in the weeks leading up to the eruption for his defiant refusal to evacuate. He had lived on the mountain for over 50 years and could not be convinced that it posed a real threat. To the news crews, he was a symbol of rugged individualism. He famously told reporters, "If the mountain goes, I'm going with it. This area is heavily timbered, Spirit Lake is in between me and the mountain ain't gonna hurt me." He and his 16 cats were buried under hundreds of feet of avalanche debris. His misunderstanding of how a volcano works was total. He did not account for a lateral blast. He did not account for the lake itself being displaced entirely, turned into a tidal wave of mud and water that scoured the surrounding hillsides bare before collapsing back into the basin. Truman represents the hubris of assuming the future will look like the past. Johnston represents the sacrifice of trying to understand what is truly coming. That 1980 event was geologically transformative. It blew 1,314 feet of elevation right off the summit. Before the blast, Mount St. Helens was a symmetrical, conical peak, the Mount Fuji of America. After, it was a gaping, horseshoe-shaped crater, a wound open to the sky. And that wound is precisely why the next explosive blast is predicted to be smaller. The mountain no longer has a solid rock lid to contain pressure. The path of least resistance is now straight up. An eruption is more likely to be a vertical plume of ash, or a slow dome-building extrusion of thick lava, like the one that occurred almost continuously from 2004 to 2008. And here, we arrive at the great paradox. A geologically less extreme eruption could produce a sociologically more devastating outcome. The deadliest weapon Mount St. Helens now possesses is not a lateral blast. It is mud. Volcanic mudflows, known as lahars, are one of the most lethal and destructive volcanic hazards. They are fast-moving slurries of rock, ash, and water that look and behave like flowing concrete. They can travel for tens of miles downstream from a volcano, destroying everything in their path. The single deadliest volcanic event of the 20th century was not a blast, but a lahar from the Nevado del Ruiz volcano in Colombia in 1985, which killed over 23,000 people. Mount St. Helens is primed for a lahar. The 1980 eruption deposited billions of cubic yards of loose ash and pyroclastic debris all over the volcano's slopes and deep into the river valleys that drain it. This sediment is unstable. It is easily eroded. All it needs is a large, sudden volume of water. That water is sitting right there, inside the crater. In the decades since the 1980 eruption, a new glacier has formed. Crater Glacier is one of the only glaciers in the United States that is actively growing. It is a massive reservoir of frozen water wrapped around the lava domes that have grown inside the crater. If even a small eruption produces enough heat to rapidly melt a portion of this glacier, or the significant snowpack that accumulates every winter, that water will mix with the loose 1980 debris. It will form a lahar. And that lahar has a direct downhill path into the North Fork Toutle River. This is the part the headlines from 2024's earthquake swarm do not capture. The apathetic green alert level does not communicate this risk. Downstream from the volcano, on the North Fork Toutle River, stands a massive piece of engineering called the Sediment Retention Structure, or SRS. Built by the U.S. Army Corps of Engineers in 1989, it is a dam designed not to hold back water, but to trap the immense volume of sediment that continues to wash down from the mountain every year. When it was built, it could hold 235 million cubic yards of this debris. But the volcano has been bleeding sediment for 46 years. That debris has steadily filled the reservoir behind the dam. The SRs has done its job. It has prevented the lower Toutle and Cowlitz rivers from silting up, which would cause catastrophic flooding in the downstream communities of Castle Rock, Longview, and Kelso. It has kept the shipping channel of the Columbia River open, but the structure is under immense strain. So much sediment has piled up that the Army Corps of Engineers has been forced to conduct a series of multi-million-dollar projects, including in 2024 and 2025, just to raise the spillway. They are fighting a losing battle against the mountain's slow, persistent erosion. The dam is nearing its capacity. Now imagine that small, lesser eruption. A minor event that melts the glacier. A wall of mud, rock, and logs comes roaring down the North Fork Toutle River Valley. It hits the already crowded reservoir of the sediment retention structure. If the lahar is large enough, it could overtop the dam's spillway. Or worse, it could cause a cascading failure. The water and sediment would surge past the dam and continue downstream. The towns of Castle Rock, Longview, Toutle, and Lexington, and the vital Interstate 5 corridor sit directly in the path of this potential flood. The population of these counties has grown dramatically since 1980. The economic infrastructure is vastly more complex and valuable. A lahar that overwhelms the SRs would be a disaster on a scale that dwarfs the direct human impact of the 1980 eruption. This is what it means for the next eruption to be worse. The geological event is smaller. The human consequence is larger. And the mountain has other ways of reminding us it is not just a passive landform. On September 16, 2025, commercial airline pilots began radioing air traffic control with alarming reports. A plume of ash was rising from the vicinity of Mount St. Helens, drifting west-northwest. An eruption seemed possible. The USGS was forced to issue a public statement to quell the rumors. There was no eruption. There were no earthquakes. There was only wind. Strong easterly winds had picked up the fine, loose ash deposited on the ground back in 1980 and lifted it into the sky, creating a phantom plume. An event that happened almost half a century ago was still capable of disrupting modern air travel and causing a public panic. The past is not gone. It is lying on the ground, waiting for a strong breeze. That sense of a persistent living past is most visceral at Spirit Lake. Before 1980, it was a pristine mountain lake, the site of Harry Truman's Lodge. The debris avalanche from the eruption displaced the entire lake in a single moment. The water sloshed up the surrounding ridges, scraping them bare to bedrock, and then fell back into the new elevated basin. It carried with it the shattered remains of tens of thousands of old growth trees. Today, 46 years later, a massive raft of those bleached, weathered logs still floats on the lake's surface. It shifts with the wind, a vast, tangled mat of ghost trees, a floating monument to the forest that was instantly erased. The lake itself is still biologically recovering. It is a scientific laboratory for how an ecosystem reboots from zero. But for a visitor standing on Johnston Ridge and looking down, it is an unsettling visual reminder of the scale of the 1980 event. It is a graveyard that still floats. The volcano's personality is not singular. It is capable of both instantaneous violence and methodical patience. The eruption that began on September 23, 2004, was the complete opposite of 1980. After a few weeks of intense earthquake swarms, the first puffs of steam and ash vented from the crater floor. But what followed was not an explosion. It was an extrusion. For the next 3.5 years, until January of 2008, a spine of hot, semi-solid dacite lava pushed its way out of the ground. It was a slow-motion eruption, advancing at a rate of about 1 cubic yard per second. It was like watching a gargantuan tube of toothpaste being squeezed. During this period, the volcano built a new lava dome inside the 1980 crater, a feature geologists call the whaleback. This dome-building phase extruded 124 million cubic yards of new rock. rebuilding a small fraction of the mountain that had been lost. It was quiet enough that scientists could work safely inside the crater, just a short distance from the active vent. The hazard was not a sudden blast, but the constant rockfalls from the unstable growing dome. This eruption physically squeezed the crater glacier, smashing it up against the crater walls and causing it to advance at the astonishing rate of 5 feet per day. It was a geological contest between fire and ice, played out in slow motion. This 2004-2008 event provides the most likely template for the beginning of the next eruptive cycle, a period of seismic unrest, a vent clearing, and then either a vertical ash plume or the slow growth of another lava dome. An event that seems manageable. An event that news cameras can film from a safe distance. An event that still has the potential to melt the very glacier that could trigger a catastrophic lahar. The job of preventing that surprise falls to the scientists at the Cascades Volcano Observatory. Mount St. Helens is one of the most heavily monitored volcanoes on Earth. A dense network of seismometers, operated by the Pacific Northwest Seismic Network, listens for the faintest tremors of moving magma. GPS stations planted on the volcano's flanks can detect changes in ground deformation down to the millimeter, tracking the mountain as it subtly swells or breathes. Gas-sniffing instruments analyze the air for telltale volcanic gases like sulfur dioxide, a key indicator that magma is rising close to the surface. Satellites use radar to map the topography, searching for any new bulges or subsidence. All this data streams into the CIVO in Vancouver, where scientists like Seth Moran parse the signals, looking for patterns. They are looking for a deviation from the baseline. They are trying to read the mountain's intentions. But even with all this technology, the one thing they cannot do is provide a long-term forecast. They can say the volcano is recharging. They can see the pressure building. They can likely give days or perhaps weeks of warning before an eruption begins. But they cannot answer the question everyone asks, when? The official USC position is clear, and has been for years. The exact timing and magnitude of the next eruption cannot be forecast decades in advance. The system is too complex. The variables are too numerous. So we are left in a state of educated uncertainty. We know the volcano is active. We saw the proof in the 350 earthquakes of 2024. We know the primary threat has shifted from blast to mud. We see the evidence in the ongoing urgent work to raise the spillway on the sediment retention structure. We know the population at risk is greater than it has ever been. We see that in the census data for the counties that line the I-5 corridor. We know the mountain's past continues to haunt the present. From phantom ash plumes that spook pilots to the ghostly log mat still adrift on Spirit Lake. We have learned so much since the fatal morning of May 18, 1980. We have better monitoring, a deeper understanding of volcanic processes, and a healthy respect for the power of a lateral blast. But knowledge can create a new kind of blindness. In focusing on preventing a repeat of 1980, are we failing to prepare for the more probable and potentially more destructive scenario of the future? The story of Mount St. Helens is now a story of infrastructure, demographics, and water. It is a slow-motion confrontation not between a mountain and a scientist, but between a mountain and an entire society's accumulated assumptions. The assumption that a dam will hold. The assumption that an emergency plan is sufficient. The assumption that because the next bang will be smaller, the consequences will be, too, for now, the green alert level holds. The summer hiking trails on the ridges surrounding the crater are open. The Johnston Ridge Observatory welcomes thousands of tourists a year to gaze into the scar left by the 1980 eruption. But beneath the surface, the process continues. The cycle of recharge is in motion. The magma reservoir is filling. The pressure is rising. The next chapter in the mountain's 300,000-year history is being written in fractures of rock miles below the ground. 3 questions hang over the Pacific Northwest. How much more strain can the aging sediment dam on the Toutle River actually take before a moderate lahar overwhelms it? When this well-documented recharge phase finally ends, will the release be a slow, manageable dome-building eruption, or a sudden glacier melting event? And what does it mean to know with scientific certainty that the greatest risk is not the spectacular explosion, but the muddy, inexorable flow that comes after it? Somewhere miles beneath the growing glacier and the 2008 lava dome, a chamber of molten rock expands. It communicates its presence only through tremors too small for us to feel, picked up by instruments standing silent vigil on the slopes. The mountain is not sleeping, it is preparing. And the water that will one day mix with its ash is already there, frozen in the crater, waiting,